At the end of this month, the FCC is to vote on all digital operation for AM stations to make it voluntary, that anyone can jump up there and go all digital. So it's very appropriate that we have someone who has been there with us today, Dave Kolesar from Hubbard Radio in Washington, D.C. He has taken over WWFD, has made it a test bed and demo site for digital AM. He's actually also, in addition to being the chief engineer, he's the program director of the gamut and chief bottle washer, landscaper. Dave, I think we could probably add a few more things there. He is the senior broadcast engineer at WTOP and WFED, and has a lot to share with us, actually. I'm going to hit the mute button in case anybody's telephone rings or something, but Dave is happy to have you talk to us. And Dave, you're going to have to unmute yourself here, first of all, and I want to turn the floor over to you to enjoy our attention.
Thank you very much for having me with you today. And yeah, you're right. I tend to do everything at the station, from toilets to towers. So, you know, let me go ahead and pull up my slides. So I'm going to share my screen. Can you see this?
Yep.
Okay, great. This is these are the slides for the presentation that Mike Raid and Mike Raid is an engineer at Xperi Corporation, and the two of us wrote a paper that we presented at NAB this year. So these are the slides from it. So I'll if you don't mind, I'll talk along to these slides because they're sort of the best summary of what we've done at WWFD. That being said, I'll just get started. First of all, I want to thank everybody for taking the time and allowing me to be with you today. It's always great to share what we've done and what we've learned. So I really appreciate everybody taking the time today. For those of you who may not know, WWFD was the first station in the United States on a full-time basis to turn off its analog signal and use its entire RF channel to transmit a digital signal. It is an AM station. It's on 820 kilohertz. It runs 4.3 kilowatts non-directional from a single tower during the day. And at nighttime, it cuts back power to 430 watts to protect WBAP in Dallas. So it's 430 watts, 2 towers at night. This is just sort of a thank you slide showing all the industry partners that have helped out and contributed time and effort and expertise to this project. For those of you who may not be familiar with the all digital AM signal, I'll just sort of go over briefly what we did here. This is sort of a summary. Within the transmitter, this summarizes our second year of operation. Within the transmitter, the most important thing to consider is the pulse duration modulator. And you need to make sure that that has an adequate sampling rate and also amplifier headroom within that transmitter. Also this year, we took a look at our antenna system. We took a look at our antenna system, and we rotated our phase of our daytime pattern. So in order to achieve Hermitian symmetry, at the amplifier, at the final amplifier of the transmitter. And that had the benefit of providing some more signal robustness, given a better load. We looked at our day and night coverage so that we could give engineers and station owners an idea as to what a usable all-digital signal might look like. We looked at power measurement in terms of the standard method of power measurement at AM stations, which many stations have delta pin diode meters that measure current at the base. Those aren't accurate for the digital AM signals, so we proposed a couple of alternate methods of power measurement. And we also took a look at some improvements to the all digital AM signal itself, and we'll talk about that, as well as some improvements in our day-to-day operations at the site. So what I consider the most exciting part of this, from an engineering standpoint, is the explorations that we did in terms of a pulse duration modulator of the transmitter. Taking a look inside, there are functionally two inputs to the transmitter when you have a digital signal. You have the magnitude component and the phase component. The magnitude component corresponds to the audio input, and the phase component of the all digital, which is also called the MA3 signal, it corresponds to the external oscillator input of the transmitter. And it's the magnitude component that has the potential to be distorted by the modulator section of the transmitter. If the sample rate is too low, you'll get aliasing. And what you see here are the two modes of digital AM, the magnitude component versus frequency, as viewed on a spectrum analyzer. On the left, you'll see the hybrid mode of HD radio, which is the mode that's currently licensed for use in the United States. And on the right, you see the all digital component. Now, the only thing that's really important to take away from these two pictures is that the all digital component, the all digital signal, the MA3 signal, has more components in the higher frequencies. So therefore, the PDM needs to be of a higher rate. So a transmitter that may work just fine on the hybrid mode of HD radio may not be suitable for the all digital mode. And that's something that we learned the hard way because we have two transmitters at WFED, and one works perfectly and one works not so perfectly. Taking a look at power handling capacity, an MA3 signal has a peak to average power ratio of 9.8 dB, and contrast that with 6 dB for standard AM. Crest factor reduction techniques in transmitters can reduce this ratio to about 8.2 dB. But this still imposes a larger requirement. You need more amplifier headroom in the transmitter. So as a result, you have to either derate your transmitter for all digital operation or have additional peak power built into the design. Now, I mentioned that we had two transmitters at the station, and the first one, this transmitter is a BEAM6A, and as it turns out, the PDM sample rate was inadequate. There are 3 sets of carriers in a MA3 system. In fact, if you don't mind, I'm just going to go back a couple of slides and show you the MA3 slide real quick. In the center, you see the primary carriers, which are first 20 kilobits of data. And then off to the sides, from 5 to 10 kilohertz up and down, you see the secondary and tertiary carriers. And this is where your enhanced data is. No worries, no worries. So just taking a look, in the center of the all digital waveform is the primary carriers, which are the first 20 kilobits. And and then you have off to the left and right the secondary and tertiary carriers, where your enhanced data is, and which allows you to get a throughput of up to 40.2 kilobits per second. And between the primary and secondary and tertiary carriers on the border, there's something called the PIDs carriers, which are sort of their data channel, the primary IBOC data logical service channel. That's what it stands for. And within these carriers, you get the track data information and also the header information that tells the receiver that this is an all digital signal. And that's important because when we take a look at our carriers through what was originally our main transmitter, BEAM6A, we see where things sort of fell apart. So the primary carriers, which are on the left, the first 20 kilobits, are distinct, they're formed, but you know, they're a little cloudy. The PIDs carriers, which are in the center, are not so good. You can see that you're going to get a lot of bit errors there. And then if you take a look on the right, the secondary and tertiary carriers are just garbage. So as a result, our first main transmitter is only capable of transmitting what's called the core mode of MA3, which is just the primary carriers. It should be noted here that since the PIDs carriers are not forming correctly, the errors caused by that break what's called fast acquisition. And fast acquisition is basically there's a header in the PIDs carriers that tell the receiver, that tells the radio to start sending decoded audio out to the speaker right away. So that means that when you tune to it within a second and a half, you get audio. As opposed to when those carriers are not present, then it takes anywhere 5, 6, maybe even 8 seconds to lock and for audio to come out. So this was not a very good result there. When you have an inadequate sample rate on your pulse duration modulator, this is what can happen. So taking a look at our new main transmitter, which is a Nautel NX5, you see that everything is well formed. Everything looks as it should. Your primary carriers are much better formed. Your PIDs carriers, which are 16 QAM carriers, are well formed and fast acquisition works. And then, of course, your secondary and tertiary carriers look good too, even though these are the ones that are most affected by nonlinearities in your antenna system, being that they're the furthest off of your center frequency. It's probably not a coincidence that as soon as we installed this transmitter, the next Nielsen book that came out, we started to show up in the ratings, because when a station was tuned, when a receiver was tuned in, like somebody would hit scan, they would find us, audio would decode right away, and people would start listening to us. Whereas with the old transmitter, people would either have a muted radio, or you would hear the hash of just the digital signal as being decoded with an analog detector. And so people would assume that there was just static there and move on. So when we got this transmitter, all of a sudden more people started listening to us. And it also should be noted that when you have the carriers distorted, like in this slide, everything interferes with each other, and your spectral mask can get pretty ugly too. And although it still meets legal requirements of NRSC2, it's not very pretty. So moving along, once we got the transmitter up and working just fine, attention then turned to our antenna system. And the hybrid mode of HD radio requires a 30 kilohertz RF channel. And the all digital mode is a bit more spectrally efficient. It only requires a 20 kilohertz RF channel. That means that any antenna system that was certified for either the hybrid mode of AM HD radio, or for that matter, AM stereo, is automatically ready for all digital operation. That also means that there might be some antennas around that were not able to be converted to HD radio in the beginning, that might be worth a second look, because the requirements are not as stringent. And in fact, WWFD was actually one of those stations. Our antennas are short. They're 72 degrees. They've got some top loading, but but in general, it was a more narrow band antenna system than that probably would not work optimally on the hybrid mode. But here we are transmitting the all digital mode just fine. Now, we wanted to sort of go for the gold, and what we wanted to do was present the best load of our antenna system to the transmitter. And you want to achieve something called Hermitian symmetry, which basically, if you look at a Smith chart, it means either a cusp left or a cusp right. You want your impedance locus to always pass through the real line on a Smith chart at right angles, and that gives you the optimal bandwidth. So we built a 60-degree phase rotation network for our day antenna, because our cusp was more or less kind of pointing up a little bit. So then we needed to rotate it so that we could present the optimal load to the transmitter. And what that means is that there's fewer bit error rates fewer bit errors hitting the receiver, and as a result, things like fast acquisition, signal robustness, just qualitatively seem to work better. Like it recovers from driving under bridges and power lines better, and this is just something that's good practice. And if you have a marginal antenna system, achieving Hermitian symmetry can make up a bit from Visuar problems, off of your center channel. So it can compensate for narrow bandwidth. So this is always a good practice. So we have to ask, well, how well does it work? And so what we've found is that in the daytime, you can pick up the full MA3 signal, the primary, secondary, and tertiary carriers, in general, out to the 0.5 millivolt daytime ground wave contour. At the 0.5 millivolt contour, you'll lose the secondary and tertiary carriers and only get the core carriers, the first 20 kilobits. But you can get that all the way out to, under ideal circumstances, the 0.1 millivolt contour, which is way into the noise if you were to listen to a comparable analog station at its 0.1 millivolt contour. So you'll lose at the half millivolt contour the enhanced carriers, and that includes things like album artwork, full stereo, and then what will happen is at the half millivolt, the receiver will blend to either mono or parametric stereo, depending on the codec you've set up within the transmitter. And of course, during critical hours, that may affect this a bit. And in general, you should only count on reception out to about the 0.5 millivolt contour when critical hours propagation phenomena comes in. And it should be noted that within the service area, within the 2 millivolt contour, the signal is really hard to break. You can drive around under bridges, under power lines, and it's in general pretty robust, including thunderstorms. I mean, you can always get an intense storm that can cause a momentary muting of the receiver, but it recovers quickly, and it's surprising. It surprised me actually how well it worked. So everybody asked, well, what about nighttime? There's one contour that needs to be noted. It's what we call the station's half NIF contour. Each station has what's called a nighttime interference-free contour, which is a calculation. And for WWFD, that is calculated to be 10.8 millivolts. Now, our half NIF contour would therefore be 5.4 millivolts. Now, we found that no matter how bad skywave propagation got, and no matter how much interference we received, our coverage never retreated further back than this half NIF contour. Now, that at times, like right at pattern change, we would find that our coverage would extend all the way out to the half millivolt nighttime ground wave contour. And then as skywave builds up, our coverage would retreat, but no further than the half NIF. But the half NIF kind of defines the minimum marketable coverage, I guess you could say. And so that's a good metric to know when you're if you ever encounter an all digital station, or if you're considering converting to digital yourself. Taking a look at sort of the things that we have to do to keep legal and keep our stations running, we had to explore areas of power measurement. Because as I mentioned before, the standard delta pin diode meters that we had used at WWFD were only reading at about 93% of our power level when we switched to the all digital mode. So the first method that we explored was we used, we basically are comparing a CW measurement. We would throw the transmitter in CW at our licensed power, and then we would measure that with either a power meter or a channel power measurement within a spectrum analyzer. So we would take a measurement with an unmodulated carrier, and then we would turn the digital on and then readjust the power so that we have this, so that we achieve the same measurement. And then that way we know that, and then that way we know that that we are making our licensed power. And so we, and then we can also compare it with our existing delta meters, and make sure that as long as our base currents are and common point are correct in CW, then we have a good confidence that things are working and things are at the proper power level in all digital. But of course, not everybody has access to a spectrum analyzer or a power meter. Those things aren't cheap. You typically have to rent them unless you're in a larger group that has them on the shelf. So we tried something old, and it turns out to be very accurate. We dug out some thermocouple RF ammeters, and what I didn't have, I found at Hamfests. And it's older and simpler. They're largely out of production, but if you got them, they're great. They're agnostic to modulation because they just measure the work done to heat a resistor. So just for good measure, we did compare them to the delta meters at CW to make sure that they were accurate. But once we flipped to our all digital signal, the meters stayed right where they were because they're agnostic to the modulation. If you've got these or can get a hold of these, thermocouple RFM meters are probably the way to go to measure your currents in your system. So we've done a couple other things. We first wanted to try to improve the listener experience or provide additional incentives for broadcasters to convert to all digital. And in December of last year, we decided to test a multicast signal on WFED. So that basically means we tried an HD2. So we put the HD2 in the secondary and tertiary carriers. While the signal was only capable of being heard on test receivers, future receivers will have this capability built into their firmware. Since the HD2 information is contained entirely within the secondary and tertiary carriers, the coverage area is generally restricted to what in the previous slides with the green were the green areas, which were basically within the 0.5 millivolt contour. So when you drive past the 0.5 millivolt contour, then your HD2 would disappear and you would only be able to hear the main channel. And of course, a big reason to do this is that an AM station could open itself up to a separately programmed second FM translator. Now, that will probably become more of an issue with once receivers are on the market, or perhaps I don't quite know the Commission's thinking, but once the vote happens, and assuming that the NPRM is approved and MA3 becomes a licensable mode of operation, then the Commission may look at the possibility of granting translators to MA3 stations to relay an HD2. So there's a couple just other tips and tricks that we did. The XGen card in the transmitter is what generates the digital signal. And our particular transmitter doesn't have a UPS option on it. So we made an adapter cable to put it on an external UPS so that every time we take a power hit, we don't reboot the XGen card. 30 or 60 seconds to reboot, and that's off air time. So by putting it on a UPS, we restrict our power blips, our outages during power blips to the length of the blip itself. We also took a look and refined our audio processing. So if you're going to process an all digital AM signal, you don't want to process it like you would with an analog station, because you want to open it up, and you want to basically give it the same approach it with the same philosophy as you would a low bit rate internet stream. You're processing something that's either 20 or 40 kilobits, depending on how you configure the system. So you want to process it accordingly and open it up. And then we also, in March of this year, started using parametric stereo on our core channel, which means that when you drive out of the 0.5 millivolt contour, instead of it blending from stereo to mono, it blends from true stereo to parametric stereo. And of course, this also means that if you do put on an HD2, you can still transmit stereo on your main channel, albeit parametrically. We haven't tried stereo on the HD2. I don't know how well that'll work, but of course, that's one of the things we're going to try. So just to wrap this up, we learned a lot of new things in our second year of our experimental authority. Not every transmitter that worked in the hybrid mode is suitable for the all digital mode, but conversely, every antenna system optimized for hybrid operations will work as is for all digital. And many antenna systems that were previously judged unsuitable for HD radio may still be able to transmit all digital with some modifications perhaps. We looked at power measurement techniques for all digital operations because they're different from analog, but we didn't find that they were overly burdensome or complicated. Innovations and improvements are still happening, such as our HD2. And of course, we're experimenting with different philosophies of audio processing. And finally, it shows, I think our second year shows that the MA3 system, it just works. It cuts through the noise and it places AM on par, both orally and visually, with other services that you'd find in a car dashboard. And that was the real motivation for doing this, because now AM looks and sounds just like everything else in the dash. And it meets the expectations of what modern listeners expect out of audio services in the dashboard. And it's hoped that our experience is going to chart a future for, or at least a competitive future for other stations in their AM operations. So with that, that is my presentation, and I'm going to figure out how to unshare my screen. There we go.
And this is Harold with a few questions.
Sure.
It's interesting, first off, on the thermocouple ammeters, of course, with normal AM, they read high with modulation since it's reading the RMS instead of the average current. So that's interesting to me. The diode meters will normally read like an absence of carrier shift. Since our AM input is still AC coupled, I'm surprised that that apparently goes down when you start transmitting digitally.
Well, yeah, I mean, I think what it has to do with is that the with the digital AM signal, you can have up to a 9.8 dB peak to average power ratio. And it seems like when you have a, I mean, I don't want to speak too much for Delta Electronics and how they built the system, because that's the system that we've tested, because that's what was in use at WWFD. we found that the meters only read 93% of true when we flipped to digital from analog. And that probably has something to do with the higher peak to average power ratio. And it just sort of puts the median a little bit lower.
And the true is based on the thermocouple meter, which normally reads high on an AM station?
The true was based on a CW. We would flip the transmitter just to an unmodulated carrier and read what our delta meters would say. So we used that as a reference, and then we also compared that unmodulated carrier, how they read on our delta meter, to how they read on the thermocouple ammeter, to make sure that those agreed as well.
Okay, just one more question before I take the whole thing over. I noticed on your credit slides at the beginning, Potomac. How does this affect antenna monitor readings?
Well, I think I got some good news for you, because our antenna monitor is an AM19. It's an old monitor, and it still works just fine. The readings sort of maybe fluctuate a little bit, but you can still read the ratio and phase just fine. And the reason that's the case is that if you recall way back at the beginning of the presentation where I put the MA3 waveform up on the slide, the unmodulated carrier right there in the middle is not only used as a phase reference for all of the other carriers, for primary, secondary, and tertiary carriers, is not only used as that, but that's what the antenna monitor is tracking.
Thank you very much.
Sure.
Do you think the FCC is going to change its translator allocations once this stuff starts going?
I don't think so. I think that the existing translator rules will still be in place. I mean, if a station wants to transmit an HD2 and there are receivers out there, and an AM station has more than one translator, this gives them the operation of separating those translators, separating the feeds to those translators. But I don't see any changes to the FCC allocation scheme.
So they'll probably continue to let you have a translator for each of your C1 and C2s, even though receivers are out there?
Well, I'm not sure I understand the question. Are you talking about an HD? Are we talking about an HD2 or?
Yes, HD3.
Oh, well, yeah, well, right now there's no option for an HD3 on.
I'm sorry, I'm in MA3.
Oh, MA3. Okay. Well, as part of our experimental authority, so WWFD does have an FM translator, and we had an FM translator when we were analog. And so under our experimental authority, we were allowed to continue to use our FM translator, because it's just a cross-service translator. Actually, as part of our experimental authority, we filed and we made the statement that the translator maintains analog service to our city of license, so that we wouldn't disenfranchise any analog only listeners. So the FCC doesn't have any issue with continuing to use an FM translator fed from a station that converts to digital.
So if you did have translators after you went MA3 on your HD2 and possibly an HD3, you think those translators will remain allowable?
Yeah, I mean, if a translator was allocated to the AM station, then I think the FCC is agnostic whether or not that AM station is analog or digital. The question that the FCC has not specifically addressed yet is whether or not the programming could originate from the HD2. And I think they'll address that question once, if they vote on this in the affirmative, and it becomes a standard mode of operation, then the FCC will approach the topic of feeding a translator from a subchannel. And the indication seemed to be that they wouldn't have a problem with that because the FM HD2s and HD3s are the precedent for that.
Dave, one of the questions here from Stony Owen asked if you'd comment on the PDM frequencies at 60 or 70 kilohertz, or what you found necessary to do.
Well, I think the PDM frequencies in the BDAM6A transmitter are, I think they're on the order of, 130, 140 kilohertz. I'm not, see, the problem is I could only read them with a frequency counter, which is not a perfect way of doing it, because part of how a PDM works is it varies the pulse width. So you can't just, I can just report on what the frequency I read on, but it jumps around a lot. So so for instance, the Nautel NX transmitter, when I plugged it in, when I plugged the PDM output into or the PDM generator into a frequency counter to try to read what it was, I was getting, on the order of over 200 kilohertz. So with that, I mean, I'd probably have to consult with the manufacturers to get a specific value of how their PDMs work, because my measurement method was imperfect. So I don't want to comment on an exact frequency that's necessary just yet. I haven't had those conversations with the manufacturers.
I would think there'd be a master clock of frequency that's being used for the logic, and then the PDM width is calculated based upon that, and the momentary audio level. But I do have another question for you, Dave. How do you determine the correct phase rotation angle when you're matching it to the transmitter? Because obviously what you see at the output terminals of the transmitter is not going to be the same as the output transistors see on the other side of the matching networks and whatever is inside the cabinet.
That is an excellent question. And basically what we did was we consulted with the transmitter manufacturer. One of the things that is interesting about, for instance, the Nautel AUI, you see the Smith chart, but they're sampling it not quite where the output amplifier is. So I needed to ask them, and that's how we came up with the rotation of 60 degrees. Now, that being said, I have to say that getting perfect Hermitian symmetry is not absolutely necessary. It's most useful when you have a bandwidth or a Viswar problem. It can improve your situation, but if your Viswar is low enough already, it's not necessary. So I don't know if that answers the question, but basically you have to consult the test data that comes with the transmitter, or you have to consult the manufacturer itself.
Yeah, I think manufacturer, because I'm imagining that certain designs are going to be a little less tolerant of a rotation that's in the wrong direction compared to what the amplifier really wants to see.
Actually,
Right.
Actually, I was going to comment about that. It seems to me when I looked at that Smith chart, basically the carrier frequency was at 50 ohms, and one side of the bandpass was slightly above that inductively and moved toward a lower resistance. The other side of the carrier frequency was slightly capacitive and moved toward the lower resistance. What that meant was the output matching network was more or less working in a symmetric mode. And that meant that the output transistors were working into a more symmetric load, which probably reduced the linear or the nonlinear distortion. I think that's what this is all about, is by working into a symmetric load, you lower the nonlinear distortion on the output transistors, and that gives you an improved bit rate. And that's something that we see in television all the time. Most television transmitters have nonlinear and linear correction. And so the way you accomplish that in this case was by simply making sure the transmitter was seeing a symmetric load.
Right, and as we know, as you travel through the transmission line, that load spins, and so it's just a matter of rotating it so that the load is symmetric at the transmitter.
That's right.
We were lucky. I wouldn't say lucky. I mean, Kintronics did a great design, did a great job in helping us retrofit this phaser. Our nighttime pattern was already Hermitian by design, but our daytime pattern, since it was just a matching network out of the tower and coming back towards the transmitter, there was not any accommodation for phase rotation in the original design. So by the way, the original phaser was a 1961 Gates phaser. It was, the station originally was born on 1370 kilohertz. It was a 500 watt daytimer. And in the 1980s, it was, the towers were reoriented and the phaser was retrofitted for 820 kilohertz. So we had tower sections bolted on top of the towers. Then we added top loading, you know, with the reorientation and the retrofitting of the existing 1370 phaser. I mean, it really wasn't pretty. So we kind of felt like if we can make digital work there, it can work anywhere.
Dave Gordon wants to know about the receiver availability. Are all the HD radios capable of reading all digital? And how are the stations getting the word out?
Yes, okay, so all HD radios with an AM section have the MA3, have MA3 capability baked into the firmware from day one. I think there might be, of course, there's always an exception that proves the rule, and I think there are a few thousand radios that are around from the way early days that won't pick it up. But basically, essentially, all HD AM section can pick up MA3, can pick up these signals. That being said, well, how does the word get out? And one of the strategies that we used was our FM translator. The station itself is it's an adult album alternative format, which, you know, is very unfriendly territory with an AM signal. And so when we got our FM translator, almost immediately, the listeners we had on the AM migrated over to the FM. So the AM was really just acting as a legal justification to keep this FM translator on the air. So what we decided to do was we took the AM all digital and then told our listeners that, hey, after this translator, you're driving around and you can hear us on the FM, great. Well, when the reception starts to fade, try 820 AM. And you could hear us for another, 20, 30, 40 miles when you're driving around. So it was a way, so that was our initial approach. We could try to bring some of our FM audience that had HD radios back to the AM because of the larger footprint, because of the much larger footprint of the signal. And then, of course, after that, we picked up new listeners through, social media channels. I can't say that we've done a big advertising push because this thing operates on a shoestring budget. So as a AAA station, word of mouth tends to be our best advertising anyways. And so we've built up an audience in that way. And I have to say that when we got our FM translator, we were running the FM translator for a couple of years before we got MA3 fully up and running properly. And it was only when we got it up and running properly that we started showing up in the ratings. We didn't show up in the ratings while we had the FM translator, but since our AM has such a much larger footprint, we were able to, I guess, capture more meters. Now, granted, we're not lighting the world on fire with this, but the fact that, you could even show up when in our market, HD radio penetration is on the order of about 25% of vehicles on the road. That's not being sold. About 1 in 4 vehicles on the road now can receive our signal. And so if you can show up in the ratings at all with those kind of numbers, you're not doing too bad. I mean, this is relatively early in the adoption game, but it's a good sign.
That seems a good place to ask the question about WIOE. John wants to know, because they disconnected, you and I talked about this earlier. He wants to know if it was lack of receivers or something technical.
That most certainly was lack of receivers. I mean, receiver penetration varies very much market to market. And I don't know in his market what the receiver penetration rate is, but it's probably not going to be as high as it is in Washington D.C., LA, New York City, where HD radio penetration is tickling 30% or above. Your results are going to vary by market, and also in our situation, we were a station that was essentially building an audience from scratch. So we didn't have much to lose and ended up creating something out of nothing. Whereas opposed to a station with an established analog audience is going to have a different strategy and timeline for conversion.
Wasn't their problem something along the line of they wanted to put an HD2 signal from AM onto an FM translator, and the FCC said no, just like they did when FM Extra, and I'm sure Lyle Henry, if he's still on, can tell us all about that, but the FCC wouldn't let you put an FM Extra signal onto a translator because they said there were no receivers available.
Well, that was the Radio 1 station.
Okay.
An HD2, so that was a different station, but they were denied a translator for that, and I think the commission's thinking on that was that the FCC was not going to grant a translator to an HD2, to an AM HD2 that was operating under experimental authority. I think what they wanted to do was wait until it became, or it would become a licensed mode of operation before approaching the translator issue.
Okay, I've confused the stations, but I remember that was an issue with FM Extra, where they wouldn't allow you to put it on an FM translator because they said, even though there were Aruba radios available at the time, and I think Lyle probably has a garage full of them, but at any rate, they said, no, there's no radios, so you can't do that.
I think the issue was the fact that it was operating under experimental authority rather than the receivers. Although I'm not privy to you know what the commission's really thinking, but based on what I've talked to, based on people that I've talked to that are in the know, that weighed heavier on the commission's thinking.
This is Brady.
Good.
I'd like to add something to this conversation. As I understand it, there aren't any receivers out there for AM HD that have the ability to have HD2 and HD3. The receiver manufacturers have to create such a thing, and they have to be put out there. Remember that HD2, HD3 and such was a development of public radio. They were the people who came up with this idea, and they were specifically about, oh, let's do this for our FM radio stations. And that fortunately happened before the receivers had gotten out there. So I think the FCC doesn't want to grant translators for an HD2 on AM that there are no receivers that can pick it up.
Well, I mean, that is certainly a valid point. And we've recorded vectors, RF vectors, and we made RF recordings of our HD2 here at WWFD to help in the certification process of new receiver designs. And of course, there's a definite time lag between when something is demonstrated for the first time and when a receiver makes it to the market. So that might be, I don't know, maybe sometime in, I don't know about next year, but maybe the year after, you might see radios just as a matter of course. When you buy them, you're able to hear an AM HD2. I believe that wasn't done. I mean, it wasn't, I don't know that Xperi knew that it was possible to do an HD2 on an AM until we tried it. And of course I tried it with an Xperi engineer who had the code written and we implemented it on the transmitter. So, I mean, the experiment at WWFD caused Xperi to take a look at the AM HD system again, which it kind of, AM research had kind of fallen by the wayside until this project happened, because they figured that I think the popular thinking there was, well, if nobody was interested in the hybrid system, or if the hybrid system is going backwards in its adoption rate, then certainly nobody would be interested in the all digital mode. And that changed when we decided to try it out. And now it's causing people to take another look at the possibilities of digital AM.
I somehow doubt it's a system for everybody all the time. Like somebody mentioned clear channel stations. I don't think that WBAP in Fort Worth, for instance, that you can pick up all over the country, would really be interested in going all digital, at least not now. But on the other hand, for somebody like me, I have an AM station. It's 1,000 watts, non-directional, 24/7, same power, 1,000 watts. And I have 4 FM translators, and they pretty well cover the same general area where you can reasonably listen to the AM signal, unless you like a lot of static and noise. So that might be, something in the future that would be pretty helpful, I think.
Yeah, And I think that different stations are going to choose to adopt this at different times. I mean, stations with that don't have much to lose with their station, if their listeners are already on a translator, or if it's a station that doesn't have any measurable audience and wants to start something new. I mean, those are going to be better candidates for to be early adopters. But I think you're going to see stations with established analog audiences and highly profitable operations, those that exist on the AM band. Those are obviously going to be, I guess we could call them, lagging indicators of digital adoption.
What
Dave,
parametric stereo you mentioned earlier?
I'm sorry, you cut off there.
What generated the parametric stereo for the outer edge you were talking about earlier?
Oh, well, that's just a different audio. That's just a different audio codec configuration that we put in the core carriers. So it's actually a mode that's available in the Xperi firmware load on our importer-exporter combo.
I suspect it's a stereo synthesizer on the receive side, right? Like an old Orban or something.
I mean, I'm not really sure what's going on under the hood. I'm much more of an RF engineer than a so I don't want to speak out of turn as to what's going on under the hood of the.
Okay. I had also one additional comment and question. I think that on FM translators, the FCC really does not want program origination, and they're considering a lack of receivers for HD2 to be, you're using it as an STL for program origination. So I think that's what they're thinking there is, are the receivers in the field upgradable? Is there a possibility of doing upgrade firmware over the air, or the next time I take my car in?
I'm not aware of the ability to transmit a firmware upgrade over the air. I know that some receivers have the ability to get a firmware upgrade at the dealer. I know that a number of radios, for instance, when Artist Experience came out, a number of dealers offered upgrades to their radios in order to implement that. So I don't know what how many are field upgradable. I would imagine that most tabletop and component receivers that are out there probably are not field upgradable, but maybe some car ones are.
Thank you.
Dave, are there any audio recordings available on the web of any of your tests?
Just what other people have posted. I know that it ended up being the only documentation of our first HD2 test with that Kirk Harnack's recording, where we surprised him with the news that we had created in HD2. I think that's the only recording on the web of that. There was one person who had air checks of WWFD on the web, but I haven't posted anything myself.
We have a couple of about interference at you mentioned the no interference contour. What's your experience? What would you expect for the so-called clear channel stations?
This is something that honestly I don't know, and I'm going to have to defer to David Layer about, because David Layer at NAB coordinated some tests with some clear channel stations in the overnight hours. And a few years back, And he has some results from that. And I probably have to refer to him there because you see, I mean, we're a Class B station, so we don't get protected skywave. So I can't personally speak to how it performs via skywave. That being said, there are people who can.
Okay. Grady wants to talk about parametric stereo.
As I understand it, the term parametric stereo refers back to the way the original FM stereo was built so that it would be fully compatible with mono receivers. I think parametric stereo for the digital environment is they take the left and the right channels and they sum them together, and you end up with this mono signal that's pretty clear, and that's what you send out as your primary signal. And then you use a few bits that you can scavenge to create an L-R signal that can then be used by receivers when they have a good signal to create a stereo image that may not be perfectly accurate, but because the mono signal is the most important thing, that's what they want to get through first. What do you think, Dave?
I think that was done for compatibility purposes.
Yeah.
So it wouldn't outlaw all the old.
I'm not saying that this is about any kind of compatibility issue in HD. I'm saying that it's similar to why that was developed for FM stereo. But in the HD world, still, if you have 20 kilobits per second that you can afford to send out and you think it's going to get there, if you want to put your mono there and then take the extra bits that you use to describe a stereo experience and put that in the less reliable portion of your bit stream, so that the first thing you lose is separation, but you still get the center channel, that might be a good idea. Now, I may not be understanding it right, but that's what
it's sort of a very short shopping list or set of instructions. Take the mono you have, which by the way came in digital bit form, and do what Harold suggested, where it's a stereo synthesizer. If you can decide this ought to come out of left or right, and this should be some band of frequencies, 1 kilobit of instructions could get you 80% of the effect. You're right, it wouldn't be accurate, but it might be very pleasing sounding, just fake stereo from mono. And we've been living with it for more than 20 years. The Sirius and XM codecs do both this spatial bit, and some of them use spectral band replication, where it's kind of like the old subharmonic synthesizer. It takes your first audio and says, something scaled to that lower or something scaled to that higher would sound pleasing too. It's not the audio you started with. Certainly some indifference of that would be quite ugly, but it's just you got some mono in reasonable shape, and let's use some bits to dress it up a little bit.
Like synthesize the old Orban.
Exactly, except it is controlled dynamically with the program. Your encoder is saying, you're going to get this audio, and here are the instructions to turn it back into something like what you started.
Yeah, the pipe is too narrow for true stereo with equal left and right detail. So obviously you sacrifice and provide a mono signal with some instructions for widening the sound stage, and that's basically what they're trying to do.
Got another question? The phase rotation appears to be an effort to get symmetrical sideband response. You still typically have falling off amplitude as you extend away from the carrier due to non-flat antenna. Is there any transmitter pre-correction for antenna characteristics like that?
Yeah, I think Nautel does do some adaptive pre-correction within the transmitter itself. So We decided to do the rotation and the flattening under the philosophy that you want to get the antenna as best as you can get it before you ask the transmitter to make up for it.
Yeah, but how can the transmitter make up for it with dynamic equalization, as it were, like we do with HD on FM, if you're not sampling the distortion, okay, at the antenna itself, past everything else. If you're doing it at the output terminals of the transmitter, then you're only correcting for the nonlinearities of the amplifier.
You're right. It's looking at the well, and it's also looking at the load, and it's looking at the reflections it's getting back. So the goal is that you want to present the transmitter with the best load possible, and the signal constellations on the transmitter do change when we did the retuning. We saw when before we had the rotation network in, the entire constellation was just sort of tilted. And so the transmitter was trying to compensate for that. And so, you know, when we, the signal constellation just ended up looking a lot better once we rotated the network.
The thing of dynamic correction, I think, may not be necessary because the antenna is not going to be changing much, but maybe during setup, it does a sweep of the impedance and determines the correction that's required. On phase rotation, I did that in the 80s on AM transmitters.
Yeah, I mean, I'm not exactly sure what Nautel is doing under the hood. I mean, but you know, it does seem to be doing some sort of correction.
And it's a problem we've always had going back when it was just the analog AM. You want to measure modulation. That seems like a simple thing. Gee, there's a port right here on the transmitter, which is wrong. The common point is probably wrong. If you went out and if you look at a scope coming off a toroid at every one of the bases, this is like a compound speaker or every tower has a different frequency response, a different phase response. And very often you would try to read these things at your studio somewhere out in the main lobe or in some terribly deep null. And just getting it to agree on amplitude, you know, it was hard to say what right was. And you'd think, gee, something empirical like the carrier cuts off, that's say 100% negative. Out in the world, you get different numbers. And to do that and then say, yeah, we also have to do this in a group delay sense or a phase sense. This is complex. The best we can do is try and get the transmitter happy with the load it sees. And they figured out pretty quickly that's not necessarily at the output of the transmitter. That's where all of the power amplifiers come together. That world needs to be, and if you get the Hermitian symmetry, that's not necessarily broad bandwidth. What it is uniform, equal and opposite reactances at the sidebands. You may hit this number at 10K, you may hit it at 20K, but it's a cool word. And I want to thank Rackley and Louis King for teaching it to us. But it also is something that even if you're not running HD, it's a better figure of merit than we ever had. For AM stereo, many of us put in AM stereo systems and we developed better mono than we had before. The AM stereo itself went nowhere, but we raised the bar and our metering got a little better. With HD, this drastically improved some plants because we just had better tools, and we had a deal where we said, look, we want it to cross 3 things at once, and that you will have arrived when you've done these things. So HD in that respect, if only because we're measuring and testing things better, has helped us a lot.
Yeah, and another word for Hermitian symmetry also is that you know, as far as the amplifiers, they're on either constant conductance or constant resistance circles on the Smith chart, and that's the real condition where the amplifiers are the happiest.
So actually, there are two different kinds of distortions here. There's a linear distortion that comes out of a filter or the antenna system, which stays constant essentially. And by putting the 60-degree phase rotation in, you basically tried to balance the linear phase distortion of the network of the antenna. Then you have the nonlinear distortion, and that comes about because you've got a digital transmitter that is basically outputting symbols at different amplitudes. And so if program content causes it to output high amplitude symbols, it heats the solid state devices up and changes their characteristics. And so, and low and other symbols might cause different characteristics, those solid state devices. So I think basically what happened was by putting the 60-degree phase rotation in, you basically did a linear, you basically compensated for the linear distortions of the transmission system. But and that helps the transmitter obviously, but I don't think actually the transmitter has any kind of nonlinear distortion, unless maybe Nautel has included something like that. And you just simply monitor the output of the transmitter with the sample to adjust the nonlinear distortion of the output amplifiers.
It may.
Go ahead. I'm sorry. I can go back a little in history. In the early days of HD radio, David Maxson put out a book called the HD Radio Handbook. I worked with him some with respect to AM applications. In the early days, when the only way to do it was the hybrid mode, since there was data in the center of the AM channel underneath the analog, Hermitian symmetry was originally developed to make the soldiers that were, the carriers on the low side of the center and the carriers that were on the high side of the center that were the same thing except out of phase. Hermitian symmetry helped them to more perfectly cancel and get rid of the popcorn noise in the background.
Yes.
We still have that today if you're transmitting AM hybrid HD. It's still useful in order to create an all digital signal that is more easily received by the HD receivers so that they use less of their error correction to create errors that are actually being transmitted by the transmitter, as opposed to errors that are being corrected that are happening between the antennas and the receivers and the consumer's receiver.
Yeah, with the hybrid system, the Hermitian symmetry definitely helps by keeping the different carriers in quadrature to each other, and so on an analog receiver, it cancels out, and in theory, you won't hear the hash. Of course, theory doesn't always, there are imperfections, and any kind of upsetting to the carriers not being in perfect quadrature are going to result in noise heard on the receiver.
How does the MA3 hold up in heavy interference situations? I mean, like down in Florida, you got a lot of lightning, and you get all sorts of static crashes on analog AM. Do you know how well this system would hold up, say, during a thunderstorm?
Yeah, I think that there hasn't been it's almost impossible to do a truly methodical study about this, but I've listened to this signal for 2 years and driving around, and I can just sort of give you my feel of what I've observed, in that it's pretty reliable, and the signal is pretty robust within, it's hard to break with a thunder or static crashes, and all that, within the 2 millivolt contour. and of course, as you get closer, further in, you literally have to have a lightning strike in your immediate vicinity to cause the receiver to mute. If you're in close enough. But I find that for most, when you're within the two millivolt contour, it's immune to a lot of that. And at worst, the radio just very briefly mutes and comes right back. It's almost like a buffering of an internet connection.
Dave, I've got a Vistian jump in my car because they wouldn't give me an HD radio when I bought the car, so I decided to go with the Vistian jump on the dashboard. Is that capable of that? And if I drive from from Florida up to New Jersey, going past your signal there, about let's assume I do it at night, and I listen to 820. Obviously, WBAP will come into a certain point. At where would be the southern end of it, or haven't you driven that part of it for that?
So at night, I can't speak to the specific radio you've got because I'm not familiar with it. But I think if it's an HD radio and it has an AM section, it should have it should be able to pick up the MA3 signal just fine. I think there might have been a few. I think some early Kenwood receivers had problems, but those only number in the low thousands. I think that were manufactured. As far as the coverage, the nighttime coverage, I would say that in general, if you want to bound it by a geographic area as to where you would pick it up, I would say it's roughly speaking, Frederick County, Maryland is pretty much the reception area of our nighttime signal. I mean, depending on conditions, it could go a lot further than that. But you're probably going to have reception within Frederick County, Maryland, except in the on the axis of our null towards WBAP.
Well, Dave, you've been in the hot seat for an hour and a half here almost, and
I'm having fun.
Yeah, certainly want to thank you for spending time with us. I'm not going to shut you off here if you want to continue, but I just wanted to let everyone know that we'll have the video of this later for those that have to go back to work somewhere. But we also have some other things that we'd like to get to, but we don't want to cut you short.
Dave, is Dave Carr still associated with your organization?
I'm sorry, who?
David Carr.
David Carr? No, we have a David Garner. Is that who you're thinking of?
Good grief, yes it is.
Yeah, David Garner, who was my boss for many years, was the chief engineer of WTOP, and now he's the EVP of engineering for Hubbard Corporate, but he's still based in DC.
Tell him hi for me sometime.
I will.
We both work for Outlet.
Okay. Yeah. And I think I met. I think I met you when you were showing off FM Extra at
yes,
at the TOP studios.
Yeah, that terrible room that we couldn't get a signal across it.
Yeah, and we tried FM Extra. We put FM Extra. We put an exciter on the WTOP auxiliary transmitter for a demonstration.
Yes, and it worked very well. Larry Bloomfield was having a.
It was a while ago because Ken Sleeman was still with us.
Yes, in fact, I stayed at Ken's house a night or two.
Oh, okay.
Well, that's good. That's good. I think, well, I know that you are in demand everywhere, Dave, because you're the one. There's nobody else doing it right now.
Well, I mean, there's a number of stations that I know have approached Xperi, and a number of broadcasters have reached out to me. I mean, so you know, I think if the FCC is going to vote on this on October 27th, and assuming that the vote is a yes, and then this becomes and then this mode is adopted, I think then you're going to see, you know, who's really interested come out, and you know, because when you don't have the regulatory uncertainty and the paperwork and engineering burden of an experimental authority, then you're going to see you know, more people who are interested in doing this just sort of come out, I guess you could say.
Yeah.
Also, the removal of the simulcast restrictions might help.
The simulcast in terms of
The limits on AM and FM simulcasting is apparently going away.
Oh, okay, okay. But yeah, I'm hoping that in the future I won't be the only one yakking about this.
Well, I certainly.
You have it.
Go ahead, Chris, or who's that?
No, go ahead, Barry.
Well, I was just going to say, I really do appreciate the fact that you're sharing all this, and the fact that you've been through so much, because it's a new area for most of us, but an area of intrigue and interest.
Sure, and thank you very much for allowing me the opportunity to get this to present this to you, and just to talk about it. I mean, I consider this was incredibly fun today. I mean, it's great just to sort of turn your brain back on and, you know, do something else other than like take readings all day.
Well, come back to us again, maybe in a couple of months, and let us know how things are going.
Absolutely. And if anybody has any questions for me, you can shoot me an email. You've got my name spelled, you know, I've got my name spelled on the screen. So my email is D Kolesar, and that's spelled on the screen. So it's dkolesar@wtop.com. Whiskey Tango Oscar Papa.